title of my talk is Does Seeing in Viewpoint Perspective Require Awareness? My name is Lange-Küttner. I'm from the UK, from the London Metropolitan University. So this is the overview of my talk. First, I'm going to say something about perspective drawings of figures in space. Second, I'm going to talk about the visual illusion and in particular about visual size illusions and the Amos room. I'm going to say something about learning to adapt figure size to spatial systems and about the discovery of spatial boundaries and spatial constraints. Most crucially, I'll explain how we used 3D models to test figure size adaptation. And these 3D models will have built-in perspective like the Amos room. And that led to perspective mapping. The conclusion is that there are layers of ability in children rather than just a stage-wise development. So first I'll talk about perspective with and without a 3D model. The earliest instruction about perspective drawing is from Alberti in 1435, and he describes different steps that you're supposed to take. So first he says, take a human figure of arbitrary height and determine the viewpoint. So in this way, the viewpoint will be on a human scale. But then remove the figure out of the picture and you're just left with the viewpoint as such. Now draw the lines from the viewpoint into the foreground, but in order to be able to depict depth, you need a second viewpoint outside your spatial system. And then you draw lines towards those very points in the foreground. And what you end up with is trapezoids. So you have all possible trapezoids in this perspective drawing, and you can see this is an area composed of trapezoids which gives the illusion of depth, and we call this perspective. Now what do you do if you have a real model that you want to draw in perspective? The problem is you can't use Alberti's instruction because you cannot remove the figure. So what Dürer and others came up with was to put a frame between the figure and themselves. They have a ready-made spatial system which they put between themselves and the figure, for instance with a grid. And in this way they either can draw on the frame itself or map perspective from the frame onto their paper, grid by grid. Now you can see that there is an intricate relationship between the figure and the space system, and that it's helpful if the figure is removed from the space system so that the space system as such can be appreciated. Now this intricate relationship between the space system and figure size is best illustrated by a psychologist who devised the Amos room. Now the Amos room is an ordinary room but with an extraordinary floor plan. So you have here a viewpoint. This is just a peephole. The viewers are not aware of the changed floor plan, and the floor plan is with a diagonal. So one side of the room is longer than the other. Now what happens is that the viewers see this room as normal because they cannot imagine and they don't know the floor plan. But what happens to them is that the perception of the figure size is distorted. So it's either very small or superhuman large or überhuman large. So this is we exploited that in studies about adapting size in two-dimensional space systems. Now children do not draw in perspective straight away. In fact, they do not draw in perspective at all. Only about 10 to 15% of the 11 to 12-year-olds draw in perspective spontaneously. So what do they do instead? They have a number of spatial systems in which they draw. So they usually start off drawing figures just into empty space, and then they start structuring space with a ground line, sometimes also with a skyline, and all of you might know that they also add the sun in one corner. So that's like the earth for them, their model of the earth as a plate. And then they start drawing areas. So here we've got a field, which is still orthogonal, like a football field. But then you have this view-specific space system that is either a closed perspective or an open perspective. And what we did, because the children do not draw those spontaneously, or the perspective systems not put spontaneously, we were drawing them for them on the piece of paper, and we were just asking them to draw 5 figures into each of these systems. Now, what did the 7-year-olds do? We gave these systems either in a logical sequence, the way I've just explained it, or in a random sequence, or as a control condition, we asked them to draw 5 figures on an empty space, 5 times on an empty space, and we call that the practice condition. So what you can see here is that they have, at 7 years, a rather small bandwidth of figure size. This is here in centimeters, and you can see that they're only diminishing the size in the logical condition. That is where the child's perception is gradually drawn into the 3rd dimension. This is not the case anymore in the 9-year-olds. They draw a diminished figure size in both the logical and the random sequence, but they discovered that if there are no spatial constraints and no boundaries, that they can expand figure size. So they continuously now draw a larger figure size when there are no spatial constraints. Now, this is also done by the 11-year-olds who draw very large when they can expand in an empty space, and they draw really small in the more constrained spatial systems. And then here you have the practice condition like in the 9-year-olds. Now, the 17-year-olds don't do that anymore. They don't expand anymore, but they still diminish the figure. So they've got a bias towards shrinking the figure, but not expanding the figure. And these are examples. So you can see that in this football field, some of the draftsmen here are drawing very small figures, which they then expand. So these are the bird view drawers. They show an excellent ability to modify figure size very flexibly. And then you have those who are constantly drawing small in those systems, but you also have 11-year-olds who do not shrink figure size at all. So they draw very large and not in proportion. Now, what we did was we asked ourselves whether we can build these models in 3 dimensions, like architectural models. So this is the first, this plateau here is the model for the empty space. This is the Earth model, where you have a ground line and a skyline in blue and in green. This is the orthogonal model, where you have an area. This is the floor plan. And here is the control model of this, where we omitted the surround. And on the next slide, you'll see why we omitted the surround. We omitted the surround because when you draw the trapezoid, like in Alberti's instruction, you have the trapezoid drawn onto the floor plan. But if you omit the surround, your whole floor is a trapezoid. So it's not just a painted area, but it is the floor, the spatial model itself. And you can see this is the result for figure size. The 7-year-olds show the steepest reduction. The 8-year-olds show some sort of habitual size, and the 9 and the 10-year-olds here show a gradual but very subtle size reduction. So the 3D models work quite well. But what was much more striking is this nearly sensational finding, because we've never had anything like that before. So what you can see here is the x-axis with the spatial systems, that is the surface, the earth, the orthogonal football field, and the trapezoid football field. And here are the two control models without the surround. And the grey columns are the 9 to 10-year-old children, and the 7-year-olds are the black columns are the 7 to 8-year-old children, and the y-axis denotes the perspective drawing systems which they constructed on their page in percent. Now you can see that the 9 to 10-year-old children draw the more perspective drawings, the more the more advanced the 3D model. But the 7 to 8-year-old children show a completely different pattern. They don't draw in perspective, but in the two models with the trapezoid areas, they draw more often in perspective than the 9 to 10-year-old children. So you can see it is very clear here for the trapezoid field boundaries, but for the trapezoid floor plan, it's even more pronounced. So that's nearly a replication within the study. So these are some examples of 7-year-olds drawing in perspective, and they show perspective mappings of various kinds. So some are drawing the floor plan and then stick in their figures, but some, they are drawing a diagonal floor plan, sometimes also a reversed floor plan. This would be the right one, that's the reversed perspective. But here you can see they are drawing full-blown three-dimensional spaces. So they are producing 3D sketches of the entire model, which is really, really what you want to see. That when somebody is trying to sketch in perspective. So in summary, this is the very first study to show that already 7-year-old children can draw in perspective. And we would explain that by the concordance or the overlap or the agreement between the visual percept, which the children are usually at that age not aware of. That is that when they look like a camera, their retinal size of an object will be smaller the further it is away, and the spatial axes will converge towards a viewpoint. So this is the retinal image, but there's a convergence or an agreement with the design of the model itself. So it's incorporated, embodied, built into the model. And we think that this shows that children, normal, neurotypical, not autistic children, can access low-level information just like adults as well, and use it in their drawing. So we would suggest that rather than a stage-wise or just a stage-wise development of perspective and from a symbolic code towards a visually realistic code, we would suggest a layered model of ability where also children have low-level vision and high-level vision, and with the appropriate cues they can actually access the low-level vision percept. Thank you very much for your attention.